Hey, what's up, guys? My name's Anna. I'm out here in the Binghamton Woods, and I'm looking for some fossils. If you guessed it right, I actually have not found any dinosaur fossils yet, but that's okay, because I found something that may be similarly as cool. I got this nice little rock here, and as you can see, we got some little circle fossils right there on the backside. Flip it over, we got some little shell imprints. I have no clue what kind of species these are, but that's totally okay. I'm also going to be talking to you about something way cooler than this rock. A group of dinosaurs called the Nodosaurs.
Alrighty, so let's jump into the Nodosaurids. The first question we can ask is, when did the Nodosaurids live? We can do that by looking at their geologic time range. These guys first evolved at the end of the Jurassic period and they went extinct at the end of the Cretaceous. Right here, we have a nice little diversity information graph from the Paleobiology database, and it shows that they first evolved there in the end of the Jurassic. They reached their greatest diversity during the middle of the Cretaceous, right where that really tall peak is, and they abruptly went extinct at the end of the Cretaceous, and that was due to the KT mass extinction. What is that, you may ask? Well, that's the extinction caused by the really large asteroid that hit Earth about 66 million years ago. It caused like widespread environmental devastation. It was super quick, super abrupt, super devastating, and it knocked out about 76% of all species on Earth, including all of our non avian dinosaurs, like the Nodosaurs, unfortunately. I'm also going to go over two other Nodosaurs that maybe you're familiar with, and I'll tell you when they kind of lived. So the first one is the Nodosaur that first evolved at the middle of the Cretaceous, right where that green arrow starts about 95 million years ago, and it went extinct at the end of the Cretaceous. The next one is the Boreapelta Mark Mitchellii, and that guy lived in the early Cretaceous period, right where that red arrow is. It first evolved about 145 million years ago. If you're kind of unsure about the Cretaceous period, you don't really know what dinosaurs lived during that time, that's okay. I'm going to tell you three well-known dinosaurs that lived among the Nodosaurs. The first one being the Pachycephalosaurus, super cool dinosaur, got those really distinctive spikes protruding right out of its skull. The next one is the Triceratops, and the last dinosaur is going to be the most famous dinosaur I think of all time, the Tyrannosaurs or the T-Rex. The next question we can ask is, where did the Nodosaurs live? So these guys lived in North America, in Asia, and in Europe. Right here, we got a map of what the world looked like during the Cretaceous period, and it shows the locality information of the Nodosaurs. All those green dots there are where Nodosaur specimens and fossils were found. You can see the highest concentration is actually in North America. So we'll go over five Nodosaurs that lived in America and Canada. The first one is the Sauropelta from Wyoming, the Nodosaurus, which is actually found in both America and Canada, and the Maiamorapelta from the Colorado area. Now, if we go across the border into Canada, we have found the Boreapelta from Alberta and the Edmontania from the Edmonton Formation. We also have some fossil evidence in Asia and Europe, but I'm not going to dive too deep into that. Also, if you're wondering, what did the dinosaurs feel? Like, what was the climate in the Cretaceous? Well, the average global surface temperature was higher than it is present day, so it was much warmer. Secondly, there are suggestions that there were warm tropical ocean temperatures, and the land surface was much wetter. So the Cretaceous as a whole was both warmer and wetter. These wetter land conditions actually provided perfect habitat for larger dinosaurs because it created things like rivers and lakes. I'm going to do a brief overview on the Nodosaur taxonomy. When you're looking at taxonomy of dinosaurs, to me especially, it gets a little confusing. There's a lot of different branches and the way things kind of split off. But the kingdom, Animalia, phylum, Chordata, clade, Dinosauria, class, Ornithischia, suborder, Ankylosaura, and finally, the family we are looking at is Nodosauridae. Right here, I found this nice little graph actually from a research paper I read, and it shows the splitting of like your armored dinosaurs there, Eurypoda, and then the splitting of Ankylosauria into Nodosauridae and Ankylosauridae. Up there, there's also a little time bar, And if you follow that down to where the nodosaurs and the ankylosaurs are, you see that the nodosaurs are actually ancestral to the ankylosaurs. So that's something that's pretty cool. I also have this another graph here. This one's a little bit more simplified, and it just shows the splitting of Ankylosauria into Ankylosauridae in our focus group, which is Nodosauridae. And I've been talking about nodosaurs, so I probably should explain what they look like. Right here, that reddish dinosaur right there is an artist's rendition of Boreapelta, and that can be generalized into what most of the nodosaurs kind of look like. So first of all, they were armored dinosaurs. They had these really thick bony plates that covered their entire back and their tail. And each individual bony plate is called an osteoderm. Secondly, they had a small head with kind of a narrow muzzle. And then their front legs were actually smaller than their hind legs. I know this picture doesn't do an amazing job of depicting that, but you just kind of got to use your imagination. Their hind legs were basically a little more broader, a little more stockier, and really used to support the weight of their body. And as you can see in that image, they had really distinctive spikes that protruded from their shoulder region. And another thing that I don't know, I just think about frequently is how did these guys defend themselves? Because they were not predators. But as you can see, they lack those bony plates on their stomach. So if these guys were flipped over, they are completely defenseless. They are toast from like any predators, complete goners. So I like to think if they were to defend themselves, they're going to hunker down and get pretty low. If this is the front of the animal and this is the back of your nodosaur, I think they're going to use their back legs for stability and really just show off all those spikes. Because imagine a predator's coming down, getting a mouthful of those bony plates. I don't think that'd be very much fun, but I'm not sure. That's just how I imagine it. Also, these nodosaurs were estimated by paleontologists to be about 4 to 6 meters long and weigh about 1.5 to 3 tons, depending on which nodosaur you're looking at. If you're not good with picturing how large something is, like I am, that's okay because I edited this nice little graph. I put a picture of myself on it. I'm about 1.8 meters tall in those shoes. So if you kind of remember how tall I am, that nodosaur is going to come right above my shoulder. And also, they're pretty long. So this is a pretty big dinosaur we're dealing with. Also, as you can see, the nodosaurs look pretty similar to the ankylosaurs. The ankylosaur is that kind of greenish dinosaur over there, while the nodosaur is the more red one. And I'm going to go over 3 observable differences. The first one being that nodosaurs lacked club tails. Ankylosaurs had these really distinct club tails that kind of protected themselves. They used it as a defense mechanism. Nodosaurs did not have that. The next one is the nodosaur skulls were generally not as short and broad like the ankylosaurs. They were narrow and longer, like I said. And lastly, the nodosaur's skull was not covered in protective plates like the ankylosaur. This picture doesn't do like the perfect job showing that, but once again, you kind of got to use your imagination and trust me on this one. Next is what did the nodosaurs eat? So these guys are herbivores, like through and through herbivores. And there's a couple ways that we can tell that they were just plant eaters. The first one is looking at their teeth morphology. The nodosaurs had larger, more bladed-like teeth, and this was really good for processing those tough plants and those really fibrous plants that they were eating. Secondly, the teeth showed that the nodosaur diet was more selective compared to the ankylosaur diet. Nodosaurs tended to consume more leaves and foliage, while ankylosaurs also ate that, but they tended to eat some fruit as well. The second way we know that these guys are herbivores is by looking at the Boreapelta. And the Boreapelta is a very, very well-preserved specimen. Like its armor is preserved, its skin is preserved, and its stomach contents is preserved. And in those stomach contents, it showed what its last meal was. And that last meal was a majority of ferns. Specifically, that nodosaur loved to eat leptosporangiite ferns. And right there, that image of a fern is actually what the modern day leptosporangiite ferns look like. I did just mention selective feeding, and you may be thinking, how do you know that? Well, in general, Narrow muzzle species tend to be selective feeders. So if we look at the modern day, we can compare deer, sheep, and horses to hippos and elephants. Our deer, sheep, and horses are narrow muzzled selective feeders, while our hippos and elephants are broad muzzled and they're less selective grazers. Secondly, we can look at the Borea pelta again, and paleontologists did a pollen analysis on those stomach contents and the surrounding rocks that surrounded the Borea pelta when it was fossilized. The study kind of resulted in the variety of pollen being much lower in the stomach than it was in the surrounding rocks. And that meant that that was evidence that nodosaurs ate a limited number of plant species and didn't just eat everything around them. So that's pretty cool. I'm going to go off on a little side tangent here about biostratigraphy, and I broke dinosaur biostratigraphy down into two questions. Are dinosaurs useful and are dinosaurs good? First, are dinosaurs useful? I would say, yeah. That's because they help establish the age of rock layers like any other fossil, and they help to correlate rock layers across different regions. And are dinosaurs good? Absolutely not. They are horrible for biostratigraphy. And I think this is why dinosaurs got the title lame in the first lecture of this semester. I'm hoping that's the only reason. But if it's not, that's okay. This is because dinosaurs lack in abundance. We don't have a lot of dinosaur fossils. Their fossil record is incomplete because they're really hard to find. They're not rapidly evolving, not common, not easily identifiable, not global, and not useful in marine environments. So everything that you need to be good at biostratigraphy, dinosaurs are not. Instead, you want to look at other groups of fossils like foraminifera, pollen, some other microfossils, and those are going to be way better. This is due to their more greater abundance, they have rapid evolutionary rates, and everything else that dinosaurs are not. Now, I'm going to talk to you about my favorite nodosaur, the Borea pelta markmitchellii. I'm going to do a little quick overview here. The Borea pelta was actually accidentally found by miners in Alberta, Canada. They were mining in an oil sands mine and they just happened to stumble across this great specimen. Here in that map, you can see Alberta is actually highlighted in that really dark green color. Second, the Borea pelta was actually deposited in a shallow sea that covered a large part of Alberta in the Cretaceous. So that sea is called the Western Interior Seaway. And I outlined Alberta there in green. And I showed with that green arrow, that's just about where Borea pelta was found. So in the Cretaceous period, that guy was sitting at the bottom of the sea. And then we found it in Alberta. And if you're wondering, how did Borea pelta get its name? Well, Borea pelta is the genus name. And markmitchellii, well, that's actually named after museum technician Mark Mitchell. He spent 7,000 hours preparing that specimen so it could look like absolutely perfect. 7,000 hours is just crazy to me. That's such a large amount of time. Secondly, I did mention that the Borea pelta had exceptional preservation, which included its skin and armor. And because it was preserved so well, we could actually determine, well, not me, as in we, but the paleontologists could actually determine what color it was when it was alive. They did that by utilizing mass spectroscopy to determine the preserved organic compounds. And those organic compounds can actually tell you the original pigments. This mass spectroscopy experiment resulted in them finding the organic compound benzothiazole. And that benzothiazole is that molecule image right there with the benzene ring, and it has the nitrogen and the sulfur. And benzothiazole is actually a breakdown of the reddish brown pigment. So they could determine that the Borea pelta was a reddish brown color, which is like so cool. That's only been done, I think, I want to say 2 other times. One of them is from the Psittacosaurus, which was found in Asia, like in the China area, which that one also had its cloaca preserved. So like that's pretty cool. That's like absolutely like so rare. Like that never happens. But yeah, finding the color of a dinosaur is not common at all. So for them to be able to do this due to the preservation state is just absolutely phenomenal. Second, you may be wondering, Why was Boreapelta preserved so well? Because that's not common. Other dinosaurs have are like never preserved that well. And that is attributed to bloat and float. So basically, Boreapelta died, unfortunately, and bloated after death. Then that carcass floated out to sea and it most likely floated for weeks before it sank. And then got so full of gas, the gases had to, be released and it caused it to sink to the seabed where it was preserved forever until paleontologists found it. I'm going to go a little bit more into detail about the bloat and float taphonic model. So taphonomy is basically everything that happens to an organism between its time of death and when it is fossilized. So the first thing that has to happen in bloat and float, unfortunately, is the animal has to die. Next, bacteria is going to immediately start to digest that body. And because the bacteria are digesting the body, it is going to fill up with gases and become bloated. Here we have an image of a Sauropelta, non-bloated, and you can see right after that bacteria has digested the body, it's going to become super round and bloated. Next, the carcass is going to get washed out to the body of water. And this can be due to a storm or scavengers or anything like that. And then once the carcass is in the water, the body is going to flip onto its back. You may be wondering, how do you know it's going to flip onto its back? Well, paleontologists who found the Boreapelta actually created a simulation using just very general physics about Boreapelta going out to sea and floating. And it showed that, due to the instability and how heavy the armor is on the back, and once it fills up with gas, it's going to flip every time and become belly up. And this is, like I said, due to the instability, the carcass will become quickly inverted. And then the gases are going to allow the body to become incredibly light. So it's just going to be like a little floaty, just floating on top of the water, and it can travel very long distances. That's why we saw Boreapelta in the middle of the Western Interior Seaway instead of really close to land. And all those gases, the body's going to get super big and super bloated, and it's just going to pop, and that body is going to burst. And then the body loses all buoyancy completely. It becomes super heavy now, and it's going to fall right to the sea floor. And that image there is from a documentary about the Boreapelta, and that's that guy falling to the sea floor. The Boreapelta actually fell to the sea floor, they think, with so much energy and so much force that when it hit the sea floor, a massive cloud of sediment just came right up and right over top of it, trapping it like instantaneously. And that allowed for no bacteria or anything, no scavengers to get to the body to further, make it decompose or tear it apart or anything. So that's really, really cool. The bloat and float taphonic model is just awesome at preserving dinosaurs or other specimens. That's all I have for you on the Nodosaurs. I really hope you enjoyed learning about them just as much as I did. If you want to check out any more information on the Nodosaurs, I suggest you look at most of these research papers are really good. There's a couple of videos and podcasts in there I would definitely recommend checking out. But thank you so much for listening.